The engineering grand challenge that I chose to research is making energy from nuclear fusion. While we have already figured out how to make energy from nuclear fission, which is splitting an atom apart to create energy, making energy from nuclear fusion is significantly more difficult. Nuclear fusion is when two heavy hydrogen isotopes, usually deuterium or tritium, are fused together to produce a helium atom and a neutron. A significant amount of energy is released from this process, much more than with fission. The amount of energy released through nuclear fusion, along with the fact that it produces zero carbon emissions and produces no radioactive waste, make this grand challenge a necessity in the pursuit of renewable energy. Nuclear fusion was first theorized in the early 1930s, specifically 1934 at the University of Cambridge. It was pursued as a possible way to make nuclear bombs, but fission ultimately took that role, and it wasn't until the late 1950s where a controlled nuclear fusion reaction actually took place. Recently, nuclear fusion has made some important leaps, most notably the Fusion Reactor Project International Thermonuclear Experimental Reactor in southern France, where it maintained a stable fusion reaction for 22 minutes. This reactor uses extremely powerful magnetic fields to contain the superheated hydrogen plasma produced through the fusion of hydrogen isotopes, where it can reach temperatures of 50 million degrees Celsius. However, this milestone is only one of many necessary steps to make fusion a cost-effective reality, as the biggest setback in fusion right now is the inability to sustain a reaction for a prolonged period of time. But the achievement of a 22-minute long reaction is a good step in the right direction. One advancement being made is the use of artificial intelligence and algorithms to better control the plasma and magnetic reactors. This has been utilized most notably in the East reactor in China. By using the AI to predict the patterns of the plasma, the East reactor has been able to have longer sustained reactions. While advancements have been made, we are still a long way from making sustainable fusion reactions a reality. Economic setbacks such as the large size of the magnets used in fusion, which can reach over 22,000 tons, and the precise alignment and control systems necessary to keep them in working order, along with the material setbacks, as no material has yet been found that will withstand the intense neutron bombardment associated with fusion reactions. But once solutions are found for these problems, nuclear fusion will be the most efficient, least polluting, and safest form of energy. Unlike many other forms of energy, namely fossil fuels, it produces zero emissions, zero solid waste, and zero radioactive waste. Most nuclear fission reactors operate at a ratio of 10 to 1 output to input of energy, and only 1 gram of fusion fuel is equivalent to burning 10 tons of coal. There are three engineering disciplines that stand out as the most pivotal in nuclear fusion. Nuclear energy, or nuclear engineering, obviously plays the biggest role in fusion technology. These engineers focus on the reaction between deuterium and tritium that produces the energy. Mechanical engineering is also an important discipline, as it's pivotal in designing the cooling systems, structural integrity, and other mechanical systems that are necessary for transferring heat energy into usable energy. There's also materials science and engineering, as this discipline is necessary to find materials that can withstand the severe levels of neutron bombardment, thermal cycling, and corrosion that will be experienced during fusion. These engineers focus on making sure the reactor can run continuously without compromising the material structure. There are other non-engineering disciplines that play a role in fusion too. Physics and computer science are the large ones that contribute to the process. Physics is important to ensure the reaction continues smoothly, and computer science is necessary for predicting how the plasma will move and keeping it contained in the reactor. I chose this grand challenge because I believe that nuclear energy is the best solution to the energy crisis that we are facing as a society. Nuclear energy has always fascinated me, and I'd love to have a career involved in it. It's definitely a career I could see myself being fulfilled in. In conclusion, nuclear fusion can be the energy of the future if we focus our efforts on advancing nuclear technology. If we can have more engineers focused on making fusion a reality, it will benefit society greatly.